Hey folks, let's get right into it. Module 1, Introduction to Statistical Mechanics and Review. So at the beginning of each of our lecture slides, I'm going to have a page of learning goals here, and each learning goal will correspond to one video. So for this first one, know the SI units discussed in class and be able to convert energy into various units. Let's go for it. So the first thing we have here is the Newton unit of force, and its base unit is a kilogram meter per second squared. Next is, let's write force right there. Next is the joule, which hopefully we remember that that's the unit, preferred unit for energy. And that has units of kilograms meter squared per second squared. And we have the Pascal, which is our standard unit for pressure. And that has units of kilogram per meter second squared. Now, I want to pause here for a moment and just think about these three. And there's a reason why I want you all to know the base unit of all of these. We're going to get into some complicated calculations in this class. And if the units don't work out, that means something was wrong in the calculation or the formula. So it's really important that we check our work with these units so that we know we did the math right. And so there's a couple things that I'm going to demonstrate how an easy way to remember these top three. So I always remember E equals mc squared for energy. I think that's a pretty easy thing to remember. And if we use our standard unit for mass, which is the kilogram, and our standard unit for speed, which is meters per second squared, you can see we arrive at that correct unit. Another equation that I like to remember to help me get these units right for unit of force, I remember work equals force times distance. We remember that work has units of joules. Hopefully you remember that from your physics or from your Gen Chem. So if we take work divided by, which is really energy divided by distance, that will give us a unit of force. So we already worked through that the unit of energy has to be a kilogram meter squared per second squared. And if we divide that by distance over to the other side, we're putting another meter right there. And you can see this meter cancels with one of those meters, and we're left with kilogram meter per second squared. So we got it correct. And then finally, the last equation that I like to remember for the Pascal that helps me out is pressure equals force divided by area. So now that we've got a clever way of working out the force unit, kilogram meter per second squared, if we divide that by the standard unit for area, which is a meter squared, you can see that's all going to work out for us, right? This meter cancels with one of those, and 1 over meters, we'll put that in the bottom there. So we just get kilogram meter per second squared. So those are all, I think, three pretty basic equations that are going to help you remember these units. So moving on, watt is our unit of power. That is a joule per second. Our amp is a rate. It's a rate of charge. And so that has units of coulomb per second. The coulomb is charge, and that has units of amp seconds. And a volt, we use that as what I'll refer to as potential. And that has units of joules per coulomb. So you can see there's some other creative ways that we could plug in that unit for volt to help us with remembering these. So the electron volt is a fundamental unit. So it technically, because it's a volt, has units of joule per coulomb multiplied by fundamental charge E. So 1 electron volt equals 1 joule per coulomb times the fundamental unit of charge for an electron or for a proton, which is actually 1.602 times 10 to the minus 19 Coulomb. So you can see the Coulomb and the Coulomb cancel, and thus 1 electron volt is 1.062 times 10 to the minus 19 joules. Okay. Gas constant, we've got two different flavors, 8.314 liter, excuse me, I was going to do the wrong one there, 8.314, that would be joule per mole per Kelvin, or 0.08206 liter ATM per mole Kelvin. And as we go throughout the semester, we'll see that we can also do this in liter bar per mole Kelvin or liter Pascal per mole Kelvin, depending on what units that we want. So Avogadro's number, hopefully you guys remember that, 6.022 times 10 to the 23 things per mole. I say things because it could be electrons, atoms, whatever you want, right? It's just a number. Okay, so Boltzmann's constant. So Boltzmann's constant has the number 1.3806 times 10 to the minus 23 joule per Kelvin. And what I want to point out here, the gas constant and Boltzmann's constant are actually one and the same thing. They are just different by Avogadro's number. So for example, if we take that 8.314 number and divide it by Avogadro's number, so if we say R divided by NA, that gives me Boltzmann's constant, which is kind of cool. Planck's constant, that's another fundamental one, 6.626 times 10 to the minus 34 joule seconds. And then finally, the wave number can be calculated in the following way. And we are going to see this unit a lot in this class, and even more so in 362. The wave number is technically 1 over lambda. You're probably used to seeing this in units of inverse centimeter from your organic chemistry days using FTIR. And we'll see that that comes from 1 over the wavelength, and when the wavelength is expressed in centimeters, we get the inverse centimeter unit. So there's a simple way that we can calculate wave number with the following relationship. So hopefully you remember this equation, E equals hc over lambda, again from your intro physics or your intro gen chem. And so now you can see the wave number is 1 over lambda. So if we divide both sides of this equation by the product hc, that will give us a wave number. So in other words, E over hc will always give us the wave number unit. And if we use joules, joule seconds, and meters per second, this will technically give us 1 over meters. So we have to include that factor of 100 to get that into the centimeter, the inverse centimeter unit. Okay, folks, that's it for this video. We will do some example calculations and unit analysis in the live lecture. I'll see you in the next video.